Okay, so the class notes are being consistently brought up here, and then this weekend I started a new link for each of these things that would be the recordings of the lectures. So if you ever need help falling asleep, you can just listen to that. I also have your first worksheet. The worksheet will be on the stuff that we're going to talk about today. I think I put the due date to be a week from today, but I think I'm going to make it a week from Thursday. Give you a couple more days to do this. But it will be something that you would upload. So you would click on the directions here. I'll just have it open up. And read the instructions, do slope fields for these. So the slope fields would be from one of these things. I was just checking these links, and some of them didn't work anymore. So you may have to search slope fields, or if you have your own computer program that does slope fields, like Mathematica or MATLAB or something, and you're comfortable with that, then you can do that. But otherwise, today I'm going to look for a few things, and I'll see if I can post it up online. So the idea is that you would generate this computer-generated graph, and you would copy it and paste it onto a file that you're going to submit to me. A Word file would probably be the best option, but if you have other files, I don't have a Mac, so I can't deal with Pages. But if you want to do it on Pages, for example, you can just save it as a PDF and upload that, and then I'd be okay with that. So you're going to be asked to create a slope field, and then given a couple of initial conditions, you would be asked to find solutions for your slope fields. I don't know if those make sense. Those terms make sense right now, but hopefully by the end of class you'll know exactly what I'm talking about. So that is the worksheet. In terms of the honors, I have the syllabus already done. I just haven't syllabus addendum finished. I just need to upload that, and then I'll share that for you, for those people that are going to be in honors for this class and linear algebra class. Okay. So those are quick announcements about the website, and now I'm going to jump on solution curves, and so we're starting chapter 2. There's a few things at the end of chapter 1 that I kind of went over very, very lightly in the last class. But what I was planning to do is I was planning to make little videos and trying to solve for a couple of more problems involved in section 1.3. So, solution curves. Oh, I don't have my notes ready here. So the idea behind a solution curve is when you have a differential equation, the ideal thing is to find the function, solving for the unknown function, right? But one of the first steps is to sometimes be able to see what your solution might look like in terms of a graph. And so for that, we're going to take a look at what's called slope fields. And the slope field by definition is a graph of slopes. And I was going to say a field of slopes, but that's how math people, you know how in English they tell you not to define the words or phrase with the actual words or phrase, but in math it's totally okay. So a differential equation, if you remember the definition, is an equation with a derivative of an unknown function that we're trying to solve for. And we talked about the order derivatives, you know, higher orders. That means there's a derivative to the third or fourth power that exists there. That would be a fourth order differential equation. For our case right here in chapter 2, we're going to focus on first order differential equations, which means the highest derivative we'll see is just the first derivative. And back in calculus, when we first talked about first derivatives, the first derivative was the rate of change. We translated the first derivative as the rate of change, as a slope of the tangent line, and stuff like that. So the idea that the first derivative is a slope is going to be our key to this idea of a slope field. So a slope field is defined to be the graph of a first order differential equation where you're able to write the differential equation as the first order differential equation as the derivative equal to something. So if you can isolate the derivative by itself equal to something, then you should be able to, hopefully, should be able to draw a slope field. Okay? Let's see if we can come up with let's use that model that we had, our E what is it, dy dt is equal to kt or ky or something. Let's put an actual value. Sorry, let's put an actual value for k. Let's just pick a number. What? Oh, 1. why don't we just take k out and let's just say 1. All right, easy enough. So this is a fairly simple differential equation, and this is your slope. So you're identifying your slope. And what you want to do is to define your slope given this expression. Now, this expression could possibly have a y and a t in it. And so what I would do is make your two-dimensional plane t and y your dependent and independent axes. And then this is kind of silly to do this, but I'm going to do it anyways. I'm going to make a table of t and y. Well, I'm sorry. I'm going to make my table a little bit differently. T, comma, y as a point that goes in my input, and my output would be my slope, dy dt. Okay? So what does that mean? That means if I were to pick a point, let's randomly pick a point here, 1, 1. If my t was equal to 1 and my y was equal to 1, what's my slope going to equal to? 1. I don't see any t's in here, so actually the t doesn't matter. So whatever the y value is going to be the slope. All right? Now, how is that going to look like in my graph? In my graph, I'm going to, at this point, 1, 1, draw a little line segment that looks like it has a slope of 1. I would draw a little line segment that looks like it has a slope of 1. So that would be 1 point, 1 slope. Now we just have an infinite number to go. T is equal to 2, y is equal to 1. This is again going to be 1, right? So that's going to be another slope that looks like it has slope 1. How about if we have t is equal to 1 and y is equal to 2? What's the slope? 2. So now I'm going to go up here and draw a slope that's a little bit steeper than the first one. Well, it's probably going to be the same deal over here. So you get the picture? Now, can you fill in the rest of this graph? So you could probably take guesses and say these things, the slope's going to get less and less steep as you go down here, go lower, lower. And then as you go out here, it doesn't matter because it doesn't depend on t. And doing this by hand is tedious and impractical, and so this is where we rely on computer programs to plot this stuff for us. Okay? All right. Well, this is, I don't know, maybe I should have chosen another example, but this is an example where there's only y by itself. And maybe we should, it's the same thing if I have a t in here. I don't want to do it. You guys can figure it out. If there's a t in there, then you do the algebra between a y and a t to get your slope, and then you would, do the same picture. Well, it won't be the same picture, but you'll do another picture. So let's actually take a look at, wait, there's another definition here, a direction field. Gives a specific direction. Oh, this is the actual definition of the. Oh. I can't bring it down lower. There it goes. All right. Yeah, so this is the formal definition of a slope field. I'm more interested in actually generating this, not by hand, but by computer. And I think this is the one that didn't work. Let's see. You can just Google slope fields or something, and then you can choose a program that would be good for you or that you think would be good. Oh, this one I was able to download as a Java thing. So let's do some examples of slope fields and just drawing them out. So here they have the x. So another thing that I'm trying to do is I'm trying to mix up the variables every once in a while to get used to different variables. But you have to understand which one's the dependent, which one's the independent variable. So in this case, the x is my dependent variable, and my independent variable is t. Okay, so sometimes you'll see it x and a y. Sometimes you'll see it like I did, y and a t, and here x and a t. And it could be any letter, n and x or n and t or whatever. So you just have to be kind of flexible in figuring some of these things out. All right. The other thing that I wanted to get that I forgot to get was I wanted to pull out the book so I can do some examples. Where's my book? And so there seems to be some website and book issues with Webassign. The bookstore has told me that the codes will be available today. They told me this last week. They would be available today. So I don't know if it's available yet, but since we're having this issue with the textbook and stuff, we're going to I'm going to take a look at when the homework's due and make sure that you have, about a week or so to complete the homework after we've established our connection with Webassign. So let's take some of these problems here. This might be one of your worksheet problems, but let me take a look at number 12 here. So our dy dx is equal to 1 minus x over, or y over x. And without doing much work, let me just pretend I'm doing this by hand. I would have my xy point that I'm going to match up on a graph, and my dy dx slope as my output. So that's an input and output. And I want to take as example maybe 1, 1. And if I have 1, 1, 1 in for x and 1 in for y, I'm going to have 1 minus 1 over 1. 1 minus 1 is 0. So I'm going to have a 0 slope right here. If I have two, 1, if I have 2 for x and 1 for y, I'm going to have 1 minus 1/2, so that's just 1/2 for my slope. I don't know. All right. So this is an example. I just wanted to do a couple of them as an example of something that has an x and a y in it, an independent and a dependent variable in the slope formula. But again, I'm more interested in doing this using the plotter here. And so I don't know if I can change a variable. They have x's and t's, so I think I'm going to keep it as x and t's and just translate my equation as dx dt is equal to 1 minus, bad operator, what? No. I guess I should finish it first. The x, the y is the independent variable, so in this program it's x, and then we'll divide it by t, and then close it. And I don't need any parameter changes or anything like that. This allows you to explore different families. So let's just take a graph of that phase of that field, and it would look something like this. So yeah, as far as your assignment would go in your worksheet, you would just copy and paste this. But I'm trying to shrink this so I can take a good picture. I'll just take a picture of it. So the idea is to just, aside from being able to generate this graph, there's a couple of other things that this worksheet is asking you. Let's just cover up this handmade stuff. Actually, we can cover this up too. So sometimes it gets a little tricky because the axes disappear, but you have to know where your origin is. That's usually an important piece of information. So let me just redraw the origin here. 0. Oh, what happened? And 0 here. So that's my t and x axis. Yeah.
What's the
we can just ignore the A and B. Oh, this A and B?
Yeah.
Oh, yeah, don't ignore that A and B. That A and B is parts of the problem that's asking you to do things. All right. So this is your slope field, and let's go to Bianca's question about A and B here. Well, before we answer this question or address what this means, this is a slope field. It tells you the direction of things, and what that means is that if you're, let's say this is like water flowing or something, or air blowing. Let's say it's water flowing. It's 2 dimensions, so we can pretend it's water. So this is water flowing, and it has arrows, so it's actually a slope in a specific direction. And you can see the arrows are all going from left to right. So regardless of how steep it is, it's always going from left to right. And so pretending that this is a water and some water flowing around it, if you drop like a piece of floating boat or whatever, I was going to say a coin, but it's just going to sink. If you drop a plastic and then it starts floating along, it'll follow a certain line. When I say line, I mean curve. It'll follow a certain line. And so let's say if I drop the coin, or not the coin, but the floating thing right here, it would follow this particular line, and this line is going to go, it's going to follow the lines. Oh, I diverted a little too much here. And then it's like going to push it. So at any particular point, this is going to push you a certain way. And once you get pushed a certain way, you're going to be in a new particular point, and then that new particular point, you're going to get pushed another certain way. And so a more interesting line might be from here. If you were to get dropped off here, you're going to follow this curve, but then it's going to start bringing you back up, and then it's going to go up like this. Something like that, right? So in doing that, you're following specific solutions. These are so this slope field is in general telling you the directions to go to find your solution. And if you take your little floaty thing and you drop it in this field, in this water, that line that you're going to follow is going to be one particular solution. Okay? So what that means, more specifically with these A and B parts, is that I'm going to do this in green and red to distinguish from the blue graphs that we were just drawing. So this gives you your initial condition. And the initial condition is going to essentially be a point. It's a given point, right? So the x value is -1/2, and the y value is 2. So what this initial condition tells you is that this is where you're going to drop your little floaty thing. So 1/2 would be right around here. 2 would be right up here. So, right? Is that right? 1/2, 2. So you would be here at this point, and then if you were to follow your slope field from this point, it looks like it's going to go up, and that's pretty boring, but that's how it goes. So this is, if you were to find the graph of this, if you were to find the equation of this, then that would be your solution to this initial value problem. So this is your DE, your differential equation. This is your initial condition, and this would be your solution. Now, finding it is another story, but at least now we can visualize it and imagine how it might look like. See?
Would you go backwards on it, back to the point, or
No, because you always want to go with the flow of the arrows.
no? Okay.
And so, and this is always going to go from left to right for us. Yeah?
Will you always be given arrows?
Hopefully, and if you're not given arrows, just assume it's going from left to right. Because these things, most of these problems are with respect to time, and time always goes forward. Yeah?
with the backwards thing, it's not exactly like going backwards, but drawing the preceding segment of it that would come before. Doing that. Is that
I don't see that as a problem. I wouldn't mark that incorrect or I don't know if I'd necessarily count it. But in general, when they talk about these things, they usually want to talk about it as going forward. But yeah, you can certainly draw the back part of that. Because that's, in terms of the function, we want the function, I mean, if we were to find a solution to this, that would be the function. That would include this. And so, yeah. So it wouldn't hurt if you draw the back part of it. Yes?
Is the slope undefined at x equals 0?
It looks like it might be. Oh yeah, as a matter of fact, if we put 0 in for x here, it'll be undefined. So it looks like we have a vertical asymptote there. So if your solutions look like they're going to be approaching x is equal to 0, then we should assume that it's not going to reach x is equal to 0 because it's an asymptote. Yes? So yeah, you can usually tell by looking at your differential equation if you're going to have an undefined slope there. Wow, good questions. Anything else? All right, let's take a look at the next one and draw this in a different color. This one, your initial condition or your starting point would be 3/2, comma 0. We're close to my first example over here. 3/2 is 1.5. 0 is right here. So it looks like it's just going to shoot up like that. So I probably wouldn't call this a straight line, because if you backfill and go back in time and go towards 0, we had those couple of comments that if you try to go backwards, that should be part of the graph. And if you go closer to 0, we know that's a vertical asymptote, so you know our graph is going to go down here. But this would be your other initial condition. So this would be another particular solution for this IVP if your initial condition was this point. Okay? All right, so that's what your worksheet is going to ask for. It's going to ask you to draw the slope field, and given one or two initial conditions, draw those one or two initial conditions. In fact, since we have that, maybe I'll just take away these other graphs. Might get confusing. So this would be more or less what I would expect. Now, how are you going to draw this on your computer? I don't know. Good luck. No, there's some programs where, and you'd have to look for them, but there's some programs where you have the given differential equation, and if you put an initial condition in there, it'll not only draw the slope field for you, but it will also draw the line, the graph, the particular solution for you. So I'll let you find that yourselves. Just do a search, and then you'll come up with all these programs that are available, and a few of those programs have initial condition options for these slope fields. All right. Any questions? Yes.
Should we care about the equilibrium point on this assignment?
I think so. I think I asked about what is an equilibrium point? When t approaches infinity? Uh-huh. Okay. Yeah, it's for this time. We'll talk about equilibrium points in a minute. Yeah. Yeah. Because just if this has part A and part B, you can just draw both of them in the same graph. You don't have to regenerate another one. All right. Does this thing have an equilibrium point, whatever an equilibrium point is? I haven't formally defined it yet. Well, what did you say? It's when t approaches infinity or something like that? Yeah, so t is the independent variable. So in this case, the independent variable is x. What happens as x goes to infinity? What's this equal to? 1? You think we should have an equilibrium point at 1? Doesn't look like it, huh? All right, well, let's see what an equilibrium point means. You guys got the idea, though, slope fields and then those initial conditions. So, to talk about equilibrium points, we need to define an autonomous differential equation. Now, a general first-order differential equation isn't really defined like this. If you remember a couple of pages ago, in general, the general differential equation looks like dy dx is equal to f of xy. By the way, you guys know what that means? It's a combination of x's and y's together on the right-hand side with math stuff on it. Like addition, subtraction, division, logarithms and cosines and sines and whatever else you can mathematically do to x's and y's put together on the right-hand side. That's a general differential equation. So, give me an example of an autonomous first-order differential equation. A specific example. 1 plus 2y is an example of an autonomous differential equation. Actually, I had an example earlier. It's about as easy as it gets, right? So this is an example of an autonomous differential equation. Okay? So basically, anything that doesn't have an x in it would be an autonomous differential equation. All right? Let's quickly take a look at the slope fields for these two examples over here. What's my slope field? So 1 plus 2 times y. Oh. 1 plus 2 times t, right? Because this is our x is our independent variable, and see, it gets all messed up already. We'll keep the display window. Should we keep the display window? Say it again? Oh. Oh, yeah. So this should be x, yeah. Let me change this window since I'm trying to make a point. I'm going to change the window to just go from -2 to 2 in my x. Hell, maybe I just go -1 to 1. All right, so I'll go with that. And so let me copy this, and then we'll talk a little bit more about this in after I get the other one done. And we'll talk about a specific distinctive feature about these autonomous differential equations, if you can't already see it. The other one is just the independent or the dependent variable. And it looks like that. Seems pretty plain. So I shrunk it down so it might be harder to see, but do you see anything distinctive about these examples of autonomous differential equations? They what? The equilibrium point, right? The term that we haven't defined yet, equilibrium point. So there's something interesting about this in that there's something pretty distinctive about coming to zero here. And there's something pretty distinctive about this line as well. If you look, I don't know if you noticed that when we were plotting this example over here earlier, if you look up and down this, maybe I'll highlight it. Where's my highlighter? Highlighter. No, I meant to do it this way. If you look across here, because your differential equation is not dependent on x, it doesn't matter what x is, it's always going to be the value depending on y. If you look across here, all these slopes are the same. So if I draw any horizontal line that captures a bunch of slopes at a particular y value, it's all going to be the same regardless of what x is. So essentially what you can do, now this might be kind of silly, but you could just take a snapshot of one of these things and have this describe your differential equation. You can essentially describe your differential equation by taking your slope field and squeezing it into just one vertical line. Right? That seems kind of interesting. Anyways, these, quote, equilibrium points here look like, in this first example, it looks like it's negative 1/2. And in this second example, it looks like it's 0. So let's formally define an equilibrium point. And it looks like the zeros of this function are the equilibrium points. So if you have an autonomous differential equation, that's just an equation with only the dependent variable involved on the right-hand side. And if you were to take that expression with a dependent variable involved on the right-hand side and set that equal to 0, that is your equilibrium point. So in our simple example, it looks like this. If we take this thing and set it equal to 0, you're going to get y is equal to negative 1/2, which is that graph that we saw. It's just negative 1/2, right? So we have, in this case, one equilibrium point for this particular differential equation. Does that make sense? Okay, so with that one point, when I say point, I mean one y value. With that one y value, there's something special about this graph with that one y value. And like I said, you can almost take this this whole graph over here and compress it to just one column. So I'm going to take a picture of one column of this. And it didn't matter where it was. And we can identify that our equilibrium point is this negative 1/2 over here, right? Now, with this equilibrium point at negative 1/2, what can you say about the arrows above it? It's increasing, going up. And what can you say about the arrows below that? It's decreasing. So, instead of looking at the whole slope field, where you're looking at the whole plane, you can compress this into just one column. And not only that, you can also just look at this and say, hey, this looks like it's an equilibrium point, and all the points above it are going to be going up, all the points below it are going to be going down, and then if you're right on that equilibrium point, that means you're just settled at that equilibrium point. You're not going to move up or down. Okay? Now, equilibrium points have special names. They sometimes are called an attractor or a repeller. Does it look like it's attracting or repelling? Repelling. Looks like all these points are trying to get away from the equilibrium point, right? Okay. So this graph over here gives us that information, whether an equilibrium point is an attractor or a repeller. I think it's called, what is it, sink and... Not sink and what? Source and sink. Sink or swim. So, important facts about equilibrium points. Our examples are really simple. We'll take a look at a couple more problems from the textbook. So, if C is an equilibrium point, then Y is equal to C is one solution if you're just going to stay at that constant level. Like that, if we were to stay at that 1/2 level, or negative 1/2 in the previous problem. If you have two critical points, then no other critical points can be in between them. Otherwise, we would have found it by setting it equal to 0. Then any solution between these critical points will remain between the critical points. So again, we'll take a look at more examples where if you're trying to find particular solutions to a differential equation, you're not going to go from one phase of the critical point and out of another critical point to another phase, whatever that means. Solutions must be strictly increasing or decreasing. So you can't have something that goes up and then goes down later in time, because it has to always increase or it has to always decrease. And if it's bounded above by equilibrium point, it's increasing, then that's going to end up being an asymptote. Critical points are asymptotes for solution curves. Okay, so let's do another example. Let's see if my notes has examples. Doesn't have examples. So let's go to the book. Autonomous first-order differential equations. They don't have examples either. Here's some. 21 through 28. Let's do an easy one. 22. So we have dy dx is equal to y squared minus y to the third. That's your differential equation. You can do the plot if you want, but I'm not going to do that anymore. Let's just go ahead and figure this out analytically, and then maybe confer with a plot. Confirm. So we'll take our right-hand side and set that guy equal to 0. Y squared minus y cubed is equal to 0. I think I can factor out a y squared and see that I have two critical points. Y is equal to 0 and y is equal to 1. So we're used to, I don't know, if you remember in calculus, you put this in, I go in calculus mode sometimes and just put this in a number line, put increasing, decreasing, and stuff like that. And the number line is usually horizontal, but if you want to do this in differential equations, you might as well get used to. A phase portrait is a vertical representation because the vertical line is your dependent variable, and your independent variable is x, and x in this case doesn't really matter, right? Because there's no x's on the other side. So this is all based on your dependent variable only, which is the vertical axis. So I got 0 and 1 as my equilibrium points. And now I want to figure out what happens here between these things to figure out whether these are attractors or repellers. And then that'll give me some idea of how my phase portraits would look like, or how my solutions to the graphs would look like. So how would we do that? We would essentially, just like in calculus when we used to find, first derivative test to find the max and mins and stuff like that, we can just try some values between them and see whether they're positive or negative. If they're positive, then they're increasing. If they're negative, they're decreasing, because that's the slope. So let's say a negative number. Let's put a negative number in here. When we put a negative number, this is positive. So for y less than 0, we have a positive times, and if we put a negative number here, minus 1 is going to be a negative number. Is that right? So it looks like my slope is going to be negative in this case. And so if I put a negative y, negative values of y, I will be decreasing. So I know that if I start off below 0, then my graph is just going to go down. And it's going to go down unbounded. Just going to keep going down. All right. Now let's try to put in a number between 0 and 1. So a y value between 0 and 1 and see what we get. So the y squared is always still going to be positive. And then if I put a number that's less than 1 here, positive number less than 1, this is still going to be negative, right? So it looks like between here, my graph will be decreasing. What does that mean? So that means if my initial condition happens between 0 and 1 in the y, then I'm going to go as far down as 0. I'm never going to get a y value that's negative because I can't get past this equilibrium point. Okay? And we'll see the graph of the slope fields with this information. Yeah? Yeah, the equilibrium points give horizontal asymptotes. Yes?
You factored y squared minus y cubed. You did it.
Oh, did I do this wrong? Oh, you guys should have told me that earlier. All right. Let's backtrack here. Thanks for catching that. So this should be 1 minus y, right? So we got same equilibrium points, and then let's start over again. So this when y is less than 0, it's going to be a positive and a positive. So this is going to be going up. When between 0 and 1, this is going to be a positive, and then positive, so it's still positive. And then bigger than 1, positive, and then now this is when we get a negative. Okay, so given that these are asymptotes, horizontal asymptotes means that if you fall in any of these spaces, if you fall in this space up here where y was bigger than 1, you're not going to get below 1 because your graph will stop you, this asymptote will stop you from hopping over to go below 1. And likewise, if you're up here, your graph will keep you from going past 0. Okay? So the interesting problems go between here and here. So if you start off over here, the 0 as your boundary, but if you're going to be increasing, you're going to have a boundary on top as well, and so you're going to get stuck below 1. You're not going to ever get past 1. So those are some of the comments that they were saying about those facts about increasing and asymptotes and bounded above or below and stuff like that. So for this particular differential equation, this is what you would get. And should we draw the thing and take a look at some of the solution curves? Yeah, let's do it. It's easy enough, right? If I can get it right. So this would be x squared minus x cubed. And I want to go past 1 for my maximum, so let's go to 3. So you can kind of see these phase planes. Think about that vertical cut. If we were to just take a column, how it would look like. It would look exactly like this drawing over here, this phase plane drawing that I have. But more interestingly, if we were to draw a bunch of solution curves, we can already begin by having asymptotes at 0 and 1. And our solution curves would either be going down like this, going up like this, or stuck between 0 and 1, going from left to right, having an asymptote at 1. Okay? All right, so just a few more pieces of terminology. We have attractor, repeller, and something that's semi-stable. And the face portrait is what I just drew. So let me redraw the face portrait for the graph, for the differential equation that we just did. Is that right? No, this one's going down, right? Okay. So an attractor is this stable. It's called a stable equilibrium. That means it's going to be approaching that value. That's why it's called an attractor, because it's approaching the value. So this 1 here, y is equal to 1, is a stable equilibrium. And if both sides are going away from it, it's a repeller, and that would be an unstable equilibrium because the graph wants to go away from that particular point. And this last one over here is half of it's going up, the other half's going up, and so one's going away, the other one's going to that point, so that's called a semi-stable. So y is equal to 0 is a semi-stable equilibrium. Okay? And this is a one-dimensional phase portrait. So if they're looking for a phase portrait, it's like taking our slope field and compressing it into one column of arrows, and then this summarizes everything. So without seeing how the slope field would look like, if I have this graph over here, I can imagine more or less what it should look like. And that's really for just special cases, and these are for what they're calling autonomous differential equations, where it's independent of the independent variable. So where the independent variable is not there. Okay? Questions? It's kind of cool, huh? Yeah. Okay, are we ready to move on? I think that's all from that section. So now we're off to the next section is our first crack at solving an actual differential equation analytically. Using math instead of just the graphs that we were just doing. We can actually use our Calc 2 skills. You guys got your Calc 2 skills back after doing the makeup? Did you forget your Calc 2 skills? So the first and simplest type of differential equation that we're going to deal with is called a separable differential equation. And we actually already solved a problem using the separable differential equation. We'll take a look at a couple more examples. And the idea is really simple. Again, it's an abuse of Leibniz notation, but it helps us solve for these things. The idea is that if you can separate the two variables from each other and write this as, what would this be? This would be g dy over f of y is equal to g of x d of x, or dx. If you're able to separate the variables this way, then you can just integrate them one by one, or on each side, and then you can get your solution, eventually solve for y there. So you integrate both sides and then solve for y. if you can. So there might be some times where you're not going to be able to solve for y, in which case, what is it called? Your solution is going to be a what? You get y by itself. You're trying to get y by itself, and you can't. And so what is it going to be? It's what? No. Last lecture. The other one, implicit. So if you're able to solve for y, then you have yourself an implicit solution. You can graph it on your graphing calculator, and everybody's happy. If you can't solve for y, then the best you can do is present the solution as an implicit solution, which means x and y are together, and you're not. If you try to solve for y, you might lose a half of a circle or or more than half of a spiral or something like that, depending on what your solution might look like. So if you can't solve for y, then you just leave it as is, and that would be your answer. Your answer is going to be an implicit solution. All right, so I had this example over here. Maybe I just, let's do that example over here. So this looks like an IVP, initial value problem. It has a differential equation, and it has an initial condition. And it looks like it might be separable. So this P of t just means P is a function of t. There's actually no t in there. It's not like, this is not P times t. So this is P of t. So let me just rewrite it to avoid confusion. Let me rewrite it as dp dt is equal to 0.15 P of t, plus 20. That's my differential equation that I'm starting with. Okay, now in terms of separating this, there's no t in there. This is, what kind of a differential equation is this? Autonomous differential equation. We have to classify these things, that's why. So you have to know what kind it is. By the way, what order is this? First order. Is this linear? You guys had questions on linear differential equations. This is linear. The P and the dp dt are the dependent variable, the function and its derivative, and you're not taking it to the second power, you're not taking the ln, or you're not taking a trig function of it. So this is a first order linear autonomous differential equation. All right, so separable means we want to try to separate. I don't see a t in there, but that's okay. I'm just going to say that this is a factor together. By the way, when you're adding and subtracting, you cannot separate that, right? You can only separate things that are factors, multiplication, division. So this whole thing has to come along on the p side. And I do that by dividing. Meanwhile, on the t side, I just have a factor of 1 left, so I can explicitly put a 1 in there, or just say dt. Okay? So now I want to integrate both sides, and I probably need to use some sort of u substitution, unless you know that if you mentally use a u substitution, you'll have a factor of 1 over 0.15. But in case that might slip, I'm going to just do it carefully. I would probably want to let u equal the whole denominator over here, 0.15 p plus 20 du is equal to 0.15 dp, and so this becomes a 1 over 0.15 when I replace that whole thing. So my integral on the left-hand side would just become 1 over 0.15 du over u, which we know is the natural log. So 1 over, I suppose I can just rewrite this. I'll just write it like this. ln of u. And the plus c we'll save for later on, right? And the antiderivative of dt is what? Is t. And this is where we want to start throwing the constants. I guess we're not quite done yet because I want to replace everything back with a p in it. So let me just take that one more step. So this is my solution. It's my general solution, but I have an initial condition. There's an IC up there, so I should be able to find a particular solution by putting in the values. Oh, another thing. Right now, this is the p is somewhere in the middle of this equation over here. So can I solve for p without losing anything? Yeah. So you might lose something if it's an ln. It's okay to solve ln and e to the x when you're trying to solve for stuff from there, because those are one-to-one functions. You won't lose anything. But if p was being squared or something like that, then when you take the square root of both sides along the way, you'll have to do that, and then you'll have generate a plus and minus. So then you lose information. So that's when you want to stay implicit with your solution. Here, right now it's implicit, but I can explicitly solve for this without losing any pluses or minuses or anything weird like that. So, but since I do have an initial condition, I can either solve for my c now, right here, right now, or I can try to solve for p and then eventually solve for c. I don't know any general rules of thumbs for that. For this case, I feel like I want to solve for the c right now before I solve for p. You could do it either way. The thing is that if I solve for p here, I'm going to start, because this is a constant, I'm going to start any constants that get attached to that constant, I'm going to start kind of merging it, so my constant is going to change. It's going to morph along the way. You guys don't know what I'm talking about. You know what I'm talking about? There's some weird things happening. Constants are funny. It's what? Yeah, so e to the c, and so I'm going to call that another constant. And so, yeah, so that's what happens if I try to solve for p right now, which is possible. I mean, I could do that. But, if you just keep that in mind, solve for it any way you want. So, but c is close to being solved for here, so I'd rather get c out of the way now, is what I'm saying. So I'm going to put in my initial conditions, which was the t value is equal to 0. When t is equal to 0, your p value is equal to 100. So I'm going to put that in right now. That's 1 over 0.15 ln of 0.15 times 100 plus 20 is equal to 0 plus c. So c is almost solved for here. And I just need to simplify this a little bit. So it looks like a 15 plus 20 is what? And I just need to, I guess, punch that in the calculator. So ln of 35 divided by 0.15 is, thank you, 0.7. I didn't have to pull out my calculator. Thanks, Elliot. So now I got my c. That's 23.7, and I just slowly peel that away. So eventually solve for this. Boy, maybe I should have solved for it first. Anyways. So ln, I'm going to multiply both sides by 0.15. 0.15 p plus 20 is equal to 0.15 times t plus, I got a 23.7 times 0.15. Anybody? 3.56. And then now I'll take this to the e power. Maybe I should have solved for it first. And then I'll take the 20 over and then divide by 0.15. So P is equal to e to the 0.15 t plus 3.65 minus 20, 5.6. Minus 20, and then divide by 0.15.
You will get that right away without using the substitution. Because you know the 1 over x, which is the instead of doing the substitution.
Oh, right here?
Yeah, if you want to solve for p, you'll get that right away.
I don't know. I just want to be careful about this. The U substitution generated this, so if you just keep that in mind, that's fine. Oh, it's 2 o'clock. All right, so this is our first crack at doing an actual differential equation analytically. So we'll do more of these, but your assignment, your worksheet assignment is to work on graphs. All right, see you guys on Thursday.